screen that the meeting is being recorded by the organizer. Fine. Continue, Harsh. Fine.
So, hello guys, carrying on the torch forward from Aryan. I'll continue with the
હર્ષ
next part of the
હર્ષ તમારા
uh,
મોબાઈલને વર્ટિકલની બદલે હોરિઝોન્ટલ કરી દો.
uh, horizon.
હોરિઝોન્ટલ હા, એટલે રોટેશન માટે કહું છું હું. રોટેશન ઓન રાખો and you keep it on horizontal way. Yes. Are you able to read now, friends? બધાને
Yes,
ધ્વનિ
ma'am.
હવે દેખાય
Yes,
છે
ma'am.
બરાબર ક્લેરિટી
Yes, ma'am.
સાથે? Fine.
Yes, ma'am.
Yes, Harsh, continue. Fine.
So, I'll begin again. Hi guys. So, carrying on the torch forward from Aryan, I'll continue with the next part of the chapter. That's property of superconductor. So that's a chapter for in consideration. That's superconductor, and I am Harsh Satish Kumar Dubey from Division C Automobile, and this is my presentation. So properties of superconductor. While superconductors have many properties like electrical resistivity, current, then effects of temperature, etc. But today, at the first, going to talk about zero electrical resistivity. So, as Aryan mentioned in the last class, that in superconducting state, the superconducting material shows zero electrical resistivity. That is, there is no force or barrier in the flow of current. So, why does this happen? So, when a superconducting material is cooled below its critical temperature, there is a drop in resistance, drops to zero, which causes this phenomena. And its example can be defined as mercury, which shows zero resistance below 4K temperature or 4.2K. In some books, it is given such. That's its critical temperature. So this zero electrical resistivity is shown by material. But why? At the very low temperature, the electrons pair up and merge into a quantum wave, spreading through the whole material. Now, many of you might think and know, some might even know what is quantum due to the movies of Marvel and many sci-fi, and some might know due to science of 11th and 12th. The quantum can be defined as due to its small size, the quantum wave becomes insensitive to the flaws in the material, and due to its small size, they are unable to slow the whole current that is opposite. That's the phenomena occurring here. But if someone asks, does this only occur in superconducting? So no, the answer is of course no, because if we take a microscopic size of a resisting of a conducting material also, in very small size the this effects do change at that level, and that of course leads to our next point in the properties of superconductor, that is persistent current, that which also refers to perpetual current which does not require any external power source. In superconductor, persistent current can be observed due to quantum effects used in the supermagnets. That is one of its property, the use applications of persistent current. But the important thing in persistent current is that how do we achieve it? So Persistent current can be achieved by two methods: by creating a superconducting state with a charge flowing in it, by changing the magnetic field around the superconductor after creating superconducting state. As you can see in here, this is how the persistent current flows. So, as Vaishali ma'am told in the previous lecture, that first we have to induce voltage in that material, and then when we stop, and due to the no opposing force of the to the current becomes the persistent current, and it flows for a very long time. Now, if we talk about superconducting magnets, as mentioned earlier, persistent current one of the application. So persistent current property is used in superconducting magnets. As I said, the superconducting magnet is made from the coils of superconducting wires. In superconducting magnets, they must be cooled down to cryogenic temperature during operation. So why do we need to do this? Due to the we need to cool down the coil to cryogenic temperature, so that we can induce a superconducting state, that is, there should be no force to oppose the flow of current in it, so that when the current flows through the magnet, it induces a really strong magnetic field, which I have mentioned in the further points. In this state, since the coil has no electrical resistance, large amount of current flows through the coil than an ordinary wire, creating an intense magnetic field. As I said, they are now what now what is the benefits or pros or merits of using a superconducting magnet uh, than an ordinary magnet? They are more cheaper to operate, as they do not dissipate heat in the windings. Also, they can produce greater magnetic fields than all. These two are the main pros which I could find on internet. They can Their usage can be seen in MRI machines, NMR spectrometer, fusion reactor, particle accelerator, etc. These are the uses of a superconducting magnet. Now here I have attached a photo of a 20 Tesla superconducting magnet. Here you can see that here there is a liquid helium space. Here is compensation coil, and here is the liquid nitrogen space. So let me explain what are the uses of this. The liquid helium space which is provided here contains helium, which is used to cool down the coil and cool the coil to a superconducting state. But why only helium? So as I mentioned earlier, that uh, helium has a critical temperature of 4.2 Kelvin, which is quite low compared to the others which materials. But the limited the limited you the limited amount of helium which we can find around us leads to the next part, that is liquid nitrogen space, which is which helps helium in reducing the temperature really low. When we use nitrogen or any other, it drops the temperature to a 77 Kelvin, and then with the less amount of mercury also, the temperature uh, will low will fall below the superconducting state in the compensation coil. here. A persistent current can not only be found in superconductors but also in some mesoscopic devices. Persistent current can also be found in resistive materials but in a microscopic samples due to size effects. As I said earlier, when we when we take small packs of a resistive material, that is microscopic samples, due to the side effects, the properties of the material decreases a lot than in big sizes. This is what occurs here, and this is where I end my presentation. So, guys, if you have any doubt or anything, you can ask.
Yes, students. Do you all get what Harsh was explaining? Everybody? He was talking about persistent current, in which once we have to set the voltage or current or the magnetic field, and hence we can induce current in that. After that, current would last with the same magnitude, and that is according to theoretical calculation. It tells that up to 10 to the power 6 years, 1 million years, the current would be as it is flowing in that superconducting loop. The reason is no resistance. The reason there is zero resistance state achieved by the material, which is called superconducting state of a material. Are you all getting, students? Theoretical calculation says that 10 to the power 6 years sudhi, suppose you have induced current 2 ampere. Let me clear the word infinite. Infinite, not in terms of 2 ampere will become 3 ampere or it will become 4 ampere. As year passes, it would become 10 ampere, 100 ampere. No, not in that way. Understood? It would be in a way that for infinite period of time, it would be as it is, like what we have started. So 2 ampere current, if you have set in the current coil or the loop, 2 ampere you will gain, 2 ampere as it is you will get after 10 to the power 6 years without decay. Getting everybody? I'm not getting anybody's answer. So what should I understand?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes,
Got it.
ma'am. Yes,
Yes.
ma'am.
Yes,
Got it.
ma'am.
One more thing I would like to tell you, that rightly he has showed a figure. हर्षे जे figure draw करी थी, that was perfectly okay, and that superconducting material is always used. Let me put the things in inverted comma. Are you all able to see me? Are you
No,
all
ma'am.
able to see me?
No, ma'am. No, ma'am. No, ma'am.
Is it now?
Yes, ma'am.
Yes, ma'am.